This is a perfectly flat wheel. If you place it on a railway track and give it a gentle push, it will roll smoothly. However, railway tracks cannot remain perfectly straight forever. When the wheel enters a curve, it tends to derail. You quickly realize that the outer rail of a curve is longer than the inner rail. Therefore, the outer wheel must travel a greater distance. But if both wheels rotate at the same speed, the train will be forced off the track. To solve this problem, you machine the wheel tread into a conical shape. The inner side has a larger diameter, while the outer side has a smaller diameter. As the wheel set shifts outward while negotiating a curve, the outer wheel contacts the rail at the larger diameter portion of the tread, while the inner wheel contacts the rail at the smaller diameter portion. Even though both wheels rotate at the same speed, the smaller diameter section travels a shorter distance per revolution, while the larger diameter section travels a longer distance per revolution. This allows the train to pass through curves smoothly without slipping. However, the conical tread also has its limits. When a train travels too fast or encounters a very sharp curve, the wheel set may shift beyond the effective range of the cone, increasing the risk of derailment. Being clever once again, you add a raised flange to the inside of each wheel. This flange acts like a safety device. Under normal conditions, it does not touch the rail. Only when the wheel shifts to its maximum allowable position does the flange contact the inner side of the rail, forcing the wheel back toward the center of the track. The flange also helps guide the train through switches. Whenever you need to move from one track to another, a set of movable switch rails is installed on the inside of the track. As the wheel flange passes through, it is guided by these switch rails onto the alternate route, allowing the train to change tracks. Congratulations, you have invented the modern train wheel.